All right, so here we are. We got universal gravitation satellites and space stations, and we kind of started talking about force due to gravity last day, where we had F big G is equal to G m1 m2 over r squared, where I'm going to sometimes default to, instead of using m1 and m2, I might use a capital M for the larger mass of a system and a lowercase m for the smaller mass in a system. And I'm going to use big G, universal gravitational constant, over r squared. But when I'm talking about these large scale systems, where we're talking about like planetary sort of scale stuff, I'm going to use subscript g for gravity. When we're near the surface of a planet, I may use lowercase g. Okay, so just to differentiate in terms of the notation. But we have mass 1, capital, mass 2, a distance of r between centers of mass, not between surfaces. And we have g equaling 6.67 times 10 to the power of negative 11. And yeah, you got to know the units, Newton meters squared per kilogram squared. Now what we said previously when we are near the Earth's surface was that E sub g, and I'm being specific, lowercase g, because we're near the Earth's surface, is mass times acceleration due to gravity times height. And you may see people write the exact same equation as E sub g equals mgh. Same, I write the E subscript g. And what we could say is that that's really just a special case. This is a special case for calculating EG when we're near Earth's surface. And we could even throw in a little such that AG, or even we could write it as the magnitude of the gravitational field, varies very little. And the reason it would vary very little is because we wouldn't have a huge variation in our altitude. We more or less stay within the shallow layer that humans live in. And if you ever think about like the shallow layer that humanity lives within, if this was Earth, the outline of that circle would be a pretty good approximation. Maybe it would be even too generous for the layer thickness of atmosphere that we can actually exist in as humans, right? Somebody told me one time, if you peel an apple, just the peel, just the skin is almost proportional to the amount of atmosphere that we can live inside of if the apple was the volume of the Earth. Like we barely have a biosphere, right? Like this is important to recognize, just the scale of what we think big is, right? So we're just barely inside the apple skin. So when we say we're going to have AG very, very little, that means, yeah, we're going to do all of our dealings, all of our business within the apple skin. So of course it's not going to vary a lot. That makes total physical sense. However, if we want to scale out and we want to think outside of our narrow little apple skin world, we might want to think about E big G. And if there's an F big G, there's probably an E big G. And I'm not going to go through the calculus of where this formula comes from, but I want to make sure that it's really clear. There's a negative sign out front. And we'll get some explanation as we go through why that negative sign makes sense and why that's all going to hash out for us. But right now, I want you to just take it as a matter of trust that we could write it as negative big G times mass 1 times mass 2 over r. And of course, r is the same as with the force formula. It's the distance between the centers of the masses of mass 1 and mass 2. And well, maybe we can do like a little bit of a tickling of the brain here, talking about where this negative value might come from. A lot of people have seen a diagram where here, if this is the sun, right here, this point is the sun. You've probably seen at some point in your life some diagram that shows a picture that's something like this. Here, look, I'll make it be like all grid-like. You can draw it after the fact if you want to. Did you get the idea? This sort of like three-dimensional grid shape. You ever seen like a diagram like this, and people's like, oh, that's warped space-time. That's the fabric of space being warped by, here, I'll just put like a little sun here, by the star. And then you even hear people say, have you ever heard of gravity wells? Everybody knows you need a gravity well to make a, I don't know, a wormhole or a black hole or something like that. A gravity well is a distortion of space-time. We can talk about general relativity if we want to, and we kind of did earlier in the course, about how space-time gets spaghettified and stretched out, distorted around gravitational point sources. And so if I was going to think about these kinds of big thoughts, I'd say, hey, it seems to me that if this is a visual representation of flat space-time being stretched as a gravity well, sort of into this new distorted form, that when I'm here, I'm a distance r1 away from that gravitational source, the sun. When I'm here, I'm at a distance r2 away from the sun. And when I'm like all the way out here, I'd be like an infinite distance away from the sun, right? Let's think about how this plays out mathematically. At position 1, according to this calculation, and I'm not going to really throw in numbers, I just want to think it out. Wouldn't it be a negative value? Negative value, right? So let's say it's negative. But since the r value is small, wouldn't the whole fraction be a big value? Right? R value is small, the whole fraction becomes big. So I would say negative and big. When I think about the gravitational potential energy at position 2, it's still going to be negative, but the r value is larger, which makes the fraction as a whole, can I just say mid? It's mid, okay? Negative but mid. When I get to position 3, where the r value becomes infinity, let's call this position 3. At position 3, it's still negative, but when r goes, everybody likes the limits. When you go to a limit of r equals infinity, what's the gravitational potential energy equal to? 0. So we could say negative, but it's actually 0, right? And so I think to myself, okay, well, if I use position 1 as my baseline, let's just say this is like my baseline, kind of like with roller coasters, we think about the surface of the Earth as the baseline, which seems to actually, we'll realize this more and more, that's kind of arbitrary, right? But let's just say that position 1 is the baseline. If I go from position 1 to position 2, wouldn't that be EG2 minus EG1? That seems reasonable, right? And if I were to do that, it seems to me I would probably be doing positive work to climb out of the hole. So let's just think about this. EG2, that's negative and mid. EG1, remember that there's a minus sign here that's part of the math, minus negative and big. If I have a negative mid-size value, really negative and a negative, plus a big value, is that going to make a positive value or a negative value? Positive. Well, you can throw in numbers, like silly numbers, right? I can say negative 3 plus 8 equals positive 5. I just made up those numbers, right? I use a small number and a mid-sized number, whatever that means, okay? What we're saying is that if I go from position 1 to position 2, I would have to do positive work. I would have to give the system energy. In other words, relative to position 1, I would have positive gravitational potential energy. And I've just arbitrarily called position 1 like my reference point, right? And so just with a little bit of like not very deep math, we can say, okay, yeah, it kind of makes sense that formula has to have a negative sign out front. Because I would have to do, just like if I raised a roller coaster up to the top of the roller coaster hill, I'd have to do positive work to get it to the top of the hill relative to the bottom of the hill. This is just like an astronomical roller coaster. Everybody cool with that? All right, so that's sort of my hand-waving explanation for why the negative sign is okay. No calculus, not even any numbers really. All right, so here I've got a mass on planet X, and I'm going to call planet X, fine, just X, and it starts off at a distance r1 away from the center of planet X, and we're going to raise it up to a new height above planet X. We'll call that new height R2. And really these R values should be relative to the centers of mass, but I'm going to say that the object is actually kind of on the small side compared to the planet. Not super, super small, but smaller. And we'll call this one mass B. Mass B. We'll call this one mass, well, let's just call it mass X, what the heck. And we can say that mass B has a value of 3.00 times 10 to the power of 3 kilograms, so 3,000 kilogram mass. We'll give this planet, we'll put it on the same order of magnitude as the Earth, 5.00 times 10 to the power of 24 kilograms. And we'll say that the radius of this planet, this isn't Earth, remember, is going to be 1.03 times 10 to the power of 4 meters in radius. But then by the time I get it all the way up to R2, it's going to be a distance of 2.00 times 10 to the power of 4 meters away from the center of planet X. Okay, so we've elevated this thing. Roughly 1 planetary radius away from where it started. And if we do a little bit of math on this one, we ask the question, how much work, because remember, we tried to do this like with no numbers, now we got to do it with a little bit of numbers. How much work does it take to just lift the box? And I've chosen planet X rather than Earth so we don't get confused by accidentally use E lowercase g and 9.81 and all that sort of stuff, right? We really are being forced to use this astronomical sort of thinking. And if we want to know how much work is done, the work that we do is equal to the change in how much gravitational potential energy this thing has. We've done this kind of thing before, like lifting objects into the back of pickup trucks in previous grades or whatever, right? And so delta EG would be, just like I said back up here, would be EG2 minus EG1. Expand that out. EG2 is negative G M1. Actually, you know what? Maybe I want to fix this a little bit because I've got an index problem. Right now I have mass 1 and mass 2, and I have radius 1 and radius 2, and over in my variables I thought about it. But over here I didn't think about it. And we all have to be cognizant of the fact that there's a before and after, and there's an object 1, object 2. And that can be a little bit of a pain in the butt to keep track of. And my variables did keep track of it, so let's address it. I shouldn't be calling this mass 1, I should be calling this mass X. And the other mass, we're going to call mass B. And then when we put it on over the fraction, EG2 would use R2. So be careful with the subscripts on those masses. It's not mass 1 and mass 2, it's mass X and mass B. And the reason it can't be mass 1 and mass 2 is because we have situation 1 and situation 2 indicated with R1 and R2, right? The two different positions. So minus negative G times mx mb divided by R1. And there's this part of me that wants to just sub in numbers, but then there's this maybe more clever part of me that wants to simplify this. So how can I simplify this? What algebra should I do so that I don't have to write as much scientific notation? Somebody help me out. What can I factor out of this binomial? Yeah. Yeah, basically everything but the R's, right? Yeah, this is nice. All right, so I can say, all right, well, I'll come back over here because I'm going to run out of space if I go down that column. So I'll pop them back over this way. The work is equal to change in gravitational potential energy, just so we don't lose that idea. But James is right. Negative G mx mb for box over nothing, actually, times 1 over R2 minus 1 over R1. And depending on the kind of person you are, you may decide to chunk this out, solve the bracket first, solve this first. For my money, I would probably put the whole thing in all at once because I feel very confident with my brackets. But I'm going to write it out, negative 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared, all times 1 over R2. R2 was the 2.00 times 10 to the power of 4 meters. Notice that these are not R squareds. That's for force, not for energy. And some people are going to square them just on impulse. Don't do that. Minus 1 over R1, which is 1.03 times 10 to the power of 4. What's that? Oh, they're masses. Oh, the masses. Oh my gosh, you're right. I forgot the masses. And I had such great layout and everything. All right. You know, you start the day thinking you're going to make your mother proud, and then you drop your masses. All right. You know what I'm talking about, Alex. All right. I didn't say which Alex. I'm glad that you just outed yourself for having dropped your masses. 10 to the power of 24 kilograms times 3.00 times 10 to the power of, what did I say, 3 kilograms times 1 divided by R2, 2.00 times 10 to the power of 4 meters minus 1 divided by 1.03 times 10 to the power of 4 meters. Holy guacamole. We got to be able to put this whole shebang into the calculator. Can you guys please give me some confirmation? I'm going to write a number. You tell me if I got it right, because I don't always have it right. 4.71109 times 10 to the power of 13 joules. Of course, I'd have to round that off to 3 sig figs, but... You got it? Nice. All right. Motion carries 4.71 times 10 to the power of 13 joules of work. All right. Now we're going to have some debate about this, and I suspect that most of the debate's going to be around whether you actually entered the data properly. All right, so that's the challenge with these guys. If you did get this number and you're ready to move on in your thinking, you can just take a moment to reflect and meditate on this bottom Fermi problem. How much are you attracted to the trees outside the classroom window right now? What information would you need to know to see if you're attracted to trees? Anybody else get this number? We're struggling? Let's do it. Did you get it? Okay, the motion carries. Okay, okay.